Hello everyone, welcome to my channel, The Big Boolean Theory. This video is part of a lecture series on operating systems, and currently we are on the second module of this course, that is process management. So within this module, we're trying to understand that how does the operating system manage the CPU by providing this abstraction of a process, right? And within the second module, we are currently on the fifth topic, that is time sharing. So now we are reaching the end of this topic. We have covered all of the videos that we wanted to. And here in this video, I'm going to summarize all that we learned, right? So at a very high level, in this topic, we talked about time sharing. As we discussed that time sharing is a concept where the operating system shares the CPU time among the multiple processes that exist in the computer system, right? And this time sharing allows us users to launch way more number of programs on a limited number of CPUs, right? So more number of programs on lesser number of CPUs. This is what time sharing helps us to achieve, right? And time sharing is implemented via this technique that is called CPU scheduling, right? CPU scheduling is a resource allocation technique where this operating system takes this resource, which is the CPU, and allocates it properly among the multiple processes which want to execute on the CPU, right? And throughout this topic, we talked about different aspects of CPU scheduling. We talked about different questions related to CPU scheduling, like why are we doing it, how we are doing it, when can we do it, and who is responsible for doing it, right? So one question is remaining that what are the scheduling policies, right? The which question, which we'll talk about in the next topic. So let's just quickly go over the different all of the videos and what have we covered in this topic, right? So we started this video by taking a more closer look at time sharing. We had already discussed about time sharing in the first module, right? But in the first video, we talked about some more detailed points about time sharing, right? So at a very high level, let me just reiterate. Time sharing is the concept via which we as users are able to run multiple processes on limited number of CPUs, right? So in this case, you can see there is just one CPU and n processes, where n is way more than n. And using this technique, the operating system runs all of these processes. So the way it happens is that uh, the operating system will frequently switch the CPU among the multiple processes, right? So the first point is that it will frequently switch the CPU among all the processes, and in it like it's like within 1 second, it could be the case that hundreds of processes get to execute. But even these few milliseconds that that each process gets is enough to make good amount of progress. Why? Because modern processors are blazing fast. They can execute millions and billions of instructions in a second. So within this few milliseconds, also thousands of instructions they execute. So frequent switching and a fast processor, combining these two, the result is that all of these processes get to execute on the CPU and make good progress, right? So it appears that all of these processes are running at the same time, which is obviously not the case. It is just that we are frequently switching between them. But nonetheless, an illusion is created that each of these processes is running at the same time, and that each of these processes has a private CPU of their own. This is called virtualization of CPU, right? This is an illusion that the operating system creates, that each process has its own CPU. This is the consequence of time sharing. So these and some other points we talked about related to time sharing in the first video, right? Then in the next video, we talked about how it originated, right? So before time sharing, in early days of computing, right? So the basis of time sharing, right? The basis of time sharing is that we have multiple processes that we would need to context switch, right? So this was not always the case that we had multiple programs. Earlier, in early days of computing, we had a single program running in the system, right? It was uniprogramming. Then we the it was realized that a single program is not sufficient to keep the resources of the system fully utilized, right? Not even the CPU and the other IO devices. A single program cannot keep all of them fully utilized. So the computing industry moved from having a single program to multiple programs. In this way, we could overlap computation and IO so that the system as a whole has a higher utilization, right? These resources are precious and they should be fully utilized. So more number of programs, basically multi-programming was introduced, where multiple programs were loaded and ready to execute in the memory, right? So this as a whole improved the system utilization. And then, so this is how we move from single programming, that is uni-programming, to multi-programming. And then there was a change that now users also began to sit in front of the computers. That was not earlier, right? Earlier in the batch computing days, the users used to submit their jobs and uh, not not interact with the computers like we do today, right? We sit in front of the terminal, and that is why response time became important. When you're using the computer, you want it to be responsive. When you're using multiple programs, all of them should give response. To meet this kind of demand, that is for a good response time and an interactive computing, this concept of time sharing arise, where the operating system would frequently switch between all of the processes, right? This frequent switching gave this illusion that all of these programs are running at the same time. So that is how the response time for the users and the processes, the programs, improved. So this is how we move from multi-programming to time sharing. We talked about the distinction between multi-programming and time sharing. In multi-programming, there is no frequent switching. There is just that there are multiple programs. In time sharing, not only do we have multiple programs, we also frequently switch between them. So the added advantage is that the response time has improved. So this is how the evolution took place from uni-programming to multi-programming, and from multi-programming to time sharing, right? Then in the next video, we started talking about CPU scheduling. So CPU scheduling is basically the technique that is used to implement time sharing. It's a resource allocation technique. As you can see in this diagram, here you can see this is the CPU and this is the CPU time, which is the resource that is in demand, right? And what the operating system does is that it carefully allocates this CPU time among multiple processes so that each process gets to execute on the CPU and make progress. So this resource allocation is the crucial part that makes time sharing possible. Then to understand CPU scheduling properly, we raised several questions. We already know like why we are doing this, because it helps us to implement time sharing. Then to understand CPU scheduling, we raised certain questions, that how we are doing it, like what is the mechanism that makes it even possible to do CPU scheduling. Then when can we do it, like what are the different time instants where it is a good idea to do CPU scheduling. Then the who question is about like who is doing it and what are the responsibilities of the entity who is doing this CPU scheduling. And the which question is about when doing the CPU scheduling, which is the next process that gets to execute on the CPU. So in this topic, we only talked about basically talked about all these questions and left out this which question, that is which process gets to execute on the CPU next. That is the subject of next topic, right? So we started talking about the how question. In the how question, the first part of the mechanism is that we have to give the control to the OS, right? So basically, this is the diagram that we saw. So if you look at this switching between two processes, so the key part in CPU scheduling is to stop one process and give control to another. So this switching is the important part. So in the context switch, there are these major activities. First thing is to transfer control to the OS, right? Because for CPU scheduling to happen, it will be done first of all by the operating system. And for CPU scheduling to happen, the operating system should have control of the CPU first of all, right? So without the control of the CPU, the OS can not do anything. So the first part is that we have to give the control of the OS of the CPU to the OS in some way, and then the operating system will select the next process that has to be executed, perform the actual switch, and then give the control of the CPU to the newly selected process so that it can execute further. So how do we transfer control to the OS? So there are two approaches that we talked about. One is the cooperative approach, the other is the non-cooperative approach. So the cooperative approach, here we basically we trust the user process to behave properly and wait for the user process to give up the control of the CPU on their own. How can this happen? This can happen if the user process makes a system call, or let's say there is some exception. When there is an exception, the user process, the control will be transferred from the user process to the operating system by the hardware. Or if there is some kind of device interrupt, then also the control is given to the operating system. So we are relying on traps. System calls, exceptions, and interrupts are different forms of traps. And whenever there is a trap, the control is immediately transferred from the process to the operating system. So in this cooperative approach, we are trusting that the user will give up the control on their own, or in some way will get it back. But this has a major drawback, is that it could be the case that the process has some bug, the program may be malicious, so it could have an infinite loop, let's say. In that case, we would never get the control of the CPU, and the operating system will never get to execute, and CPU scheduling would not be possible. And when such a situation arises, the only option we have is to reboot the system, right? Because we are not getting the control. We means operating system. So this was the cooperative approach, and it has a major flaw. It was only used in earlier systems. So then we talked about the non-cooperative approach. In the non-cooperative approach, we do not rely, or we do not trust the user process. We have some external mechanism, and that is the timer interrupt. So in the non-cooperative approach, we have to devise some mechanism where we will, if there is no event that transfers the control of the CPU from the user process to OS, there needs to be some other mechanism, right? So there we said that we need support from the hardware. From the hardware, we need a timer interrupt. So the timer interrupt is basically just like any other interrupt, but what it does is that the timer is programmed to raise an interrupt at a fixed interval, right? After every fixed interval, the timer interrupt raises one. So the way it works is that during boot time, the operating system starts the timer, right? It also registers the interrupt handler and those things. It starts the timer, and it is like after every clock tick, the timer decreases. Once it reaches zero, it raises an interrupt, and it is handled like any other interrupt. We have talked about device interrupts. When there is a timer interrupt, the control is immediately transferred to the operating system, and then the operating system can perform CPU scheduling. So now we have an explicit way from which is like from the hardware, and we have a guarantee that the control will be eventually back to the operating system after every fixed interval. There could be the case that we do not require timer interrupt. There was a system call or exception or some other device interrupt, and the control was transferred automatically. But if none of these things happen, in the absence of these events, we still have an explicit timer interrupt, which gives us the guarantee that the control will definitely come to the OS after every fixed interval. And in that time, whenever the control is transferred to the OS can perform CPU scheduling, right? So this was the first part, that is how do we give the control of the CPU to the OS. We can Earlier we used to rely on the user process, that is the cooperative approach. Nowadays we rely on the timer interrupt, the non-cooperative approach. Then finally, when the control is with the OS has to perform the switch. That is why we talked about the context switch. This is the most important part in the overall CPU scheduling, right? That is switching from one process to another. How does that happen? So we talked about this, that during a context switch, what the operating system does is that it saves the state of the currently running user process, right? It saves all of the registers, because registers contain the execution state. As the user process executes instructions, it builds up the state in the registers, right? So it takes a snapshot of the registers and saves them in the process control block. There is a data object called context, which is a set of registers. That is where the operating system saves the registers. This context is inside the PCB. So now once the registers are saved, what the operating system does is that it restores the context or the set of registers for the next process which is going to execute. So this idea of saving registers and loading new registers helps to pause a program and later on resume from exactly the same point, right? So this is like I give an analogy that it is like reading multiple books, right? So if you're reading a book and you want to switch to some other book, what do? You put a bookmark in the current book which you are reading, and this helps us to save the page number at which you're reading, so that now when you go back, go to other book, right, you can read the other book, and when you come back, so you can resume exactly at the same point, right? And this you can do for all the books. You can have a bookmark for each book, and you can switch between them. So whatever is the case, the key idea is that a bookmark allows us to save the state. The state is the page number, and it allows us to save the page number, and later on this bookmark is useful when we want to resume the reading from the same point, right? That is why this is very similar to what happens during a context switch. When we are taking a snapshot of the registers, this is like taking a bookmark. So once we have saved the registers, we can be sure that at a later point in time, we can resume the execution from exactly the same point that we had left. So a context switch is essentially saving some registers and loading the registers of the next process. So this was about context switch. So this basically completed the discussion that how the context switch happens, what is the overall mechanism, like how we give the control of the CPU to the OS, and how does the OS then make the switch. So once the how part is done, we now have a mechanism. Basically, we now have a setup that makes context switching possible. So then we can, when then we talked about some other questions like when do we schedule the CPU, right? So we saw this slide that there are several opportunities when the operating system can do the scheduling. So for example, when a process terminates, right, then we definitely have to give the control of the CPU to some other process because that process no longer will execute. The other example is that the process, let's say, blocks, it goes to waiting state. Even if you give the CPU, it will not be able to execute further. Then the process could be interrupted due to some device interrupt, or it could make a system call. In both of these cases, the control will go to the operating system. The operating system can deal with the interrupt or the system call, and after that, instead of giving the control back to the same process, it can run some other process also. So these are the different events during which the CPU scheduling can happen. Now, there is a distinction between these cases. The first two cases are the one where the process cannot be executed further. Even if you give the control of the CPU to the processes, they will not be executed further because in first case it has terminated, in the second case it has blocked. And the other two cases where the process was interrupted or it made a system call, here the process is very well ready to execute. If you give the control of the CPU, it can execute. Now, depending on whether the operating system decides to do scheduling only when the process cannot be executed further or not, there are two types of scheduling, that is non-preemptive scheduling and preemptive scheduling. If you're doing scheduling, basically if you're switching from one process to another only when the current process can no longer execute, then that is a scenario, or that policy is known as non-preemptive scheduling. Here basically the operating system is allowing the process to execute as much as it wants. It is being nice. Whereas if we do scheduling in all of these cases, right, particularly in these two cases, when even if the current process can execute further, but we are not allowing it to execute further, we are taking away the control of the CPU, we are preempting the CPU from the process. This approach is known as preemptive scheduling. Here the operating system can take away the control at any point, right, even if the process has instructions left to execute. So this was about when or at what points or when can we do the CPU scheduling. And depending on when we do, there are two types of scheduling. One is preemptive, other is non-preemptive. Finally, in the last video, we talked about who does this scheduling. So basically, there is a software component which is known as the scheduler, which is responsible for doing CPU scheduling. It maintains several queues, that is the ready queue and a set of wait queues. And from the ready queue, it basically selects the next process that has to be assigned the CPU. So the scheduler has a few decisions to make. First of all, whether to switch or not, and if it decides to switch, then which process to switch to. So it uses a scheduling policy, which is some kind of algorithm optimizing for some kind of goal like high throughput or a better response time. So these are all the responsibilities of the scheduler, and it is this scheduler that is responsible for doing this CPU scheduling. And we talked about the overall flow of how the process like moves from different states while their lifetime, right, and how they move through the different queues, how they migrate among the different queues, transition between different states, right. So all this we talked about the behavior of the user process and how the scheduler schedules them to the CPU. So this was about the who question. So this is what we covered in this topic, right? So now the time sharing topic is done, and we talked about CPU scheduling and the different questions. One last question is left, that is the which question. In the which question, basically we are trying to understand to which process should the control of the CPU be given to, right? And for that we have different algorithms which are called CPU scheduling policies, and we are going to study about these policies in the next topic. We are also going to see what are the different criteria which the operating system tries to optimize for, and what are the different algorithms which try to like optimize different types of criteria like high throughput, response time. And that is the last topic in process management. After that, process management will be over, right? So let's jump to the next topic where we are going to finally talk about CPU scheduling, right? So guys, this was it for this video. Thank you very much for watching, and I will see you in the next video. Thank you.